the North American Fast Information Processing Society, and distinguished lecturer of the IEEE, Computer Intelligence Society, and the ACM, and well, he's Vice President for Publications of the IEEE, the Computational Intelligence Society, and a lot of many honors. And I would like to Professor Perret to begin his talk this afternoon. Thank you.
Thank you. Thank you. I'm glad to be here, of course. And I never like to have the title slide, you know, on the presentation. This is, how many of you know about Talk Like a Pirate Day? There were some great Chilean pirates, you know. So this is September 19th every year. It's an official international holiday, and we celebrated heavy duty in Columbia, Mo. So anyway, and my talk is going to have the title Streaming Consciousness, and I grew up in the 1960s, you know, power to the people, you know, kind of thing. And so this just reminds me of what, you know, streaming consciousness should be all about. So I'm going to talk about streaming clustering, you know, and this is going to be my streaming consciousness about this particular topic. I'm from the University of Missouri, and like Ringo Starr or Joe Cocker, I get by with a lot of help from my friends, because I don't do hardly anything anymore. And who are my friends this time? Well, you've already heard this guy. You know, we're pretty much connected together there. And then these are two of my PhD students who do most of the hard work. And I just talk about it. So you might wonder where the University of Missouri is if you've never been in the middle of the United States. So here's the United States. And if you look there, there's two major river systems. The Mississippi River goes, you know, north to south. And then the Missouri River connects together, and right at the join of those two rivers is the city of St. Louis, which is close to where I'm at. You know, it's the edge of the state of Missouri. So there's the Mississippi River coming down, and there's St. Louis right there. And my city, Columbia, is right in the middle between St. Louis and Kansas City, the other big city in Missouri, about as far from the ocean as you can imagine in the United States. And this is what it's like, this is what being at the University of Missouri is all about, real football. Real football, that's... Okay, so why streaming data? Why am I interested in streaming data? Well, you know, all the clicks on the web now, you know, it's just ubiquitous, just continuous streams of information coming in. And of course, there was a big push for data mining going on there. And of course, for me personally, it's because of the ubiquity of sensors now. You know, we've got sensors everywhere. They're cheaper, they measure so many different things. And, you know, this guy, Lotfizadeh, the guy who created fuzzy set theory, predicted this back in the mid-1990s, that one of the components of what he was calling recognition technology was actually the fact that the sensing was going to become so much cheaper and so much more plentiful, and that's going to give rise to this new realm of recognition capabilities. And we need to make decisions in real time as the data is arriving. Now, you can't wait in many cases till later. Well, that was the paper. So here's why am I interested in streaming clustering? Well, we have a big group, a center for technology for elder care, taking care of us old people, right? Because what you want to do is you want to make sure that mom and dad and you know, Jim and Jim are safe and yet independent, right? So you've got to somehow watch what they're doing, non-invasively, hopefully, and make decisions, make sure that they're okay, right? So we stick sensors all over people's apartments, right, in some of these elder care facilities. I'll talk a little bit more about that tomorrow. And we want to know what are the normal activities that the person is doing. Are they doing their normal activities? What are the outliers? You know, if you fall down, that should be an outlier, right? You should be able to issue an alert. And people change over time. And so the baseline, what was true today for me, probably won't be true 2 months from now, you know, because things change, right? And so what we're seeing here is a plot, the principal component analysis projection down in the 3 space of a 32-dimensional feature vector that was extracted from these sensors, from motion sensors, and we have a bed sensor that we collect heart rate and respiration, other parameters in there. We think we can get sleep stages and blood pressure now too. And so, you know, just looking at this, you know, as Jim did this morning, he says, oh, you know, if you look at this, you can see there's some structure to this data, even in the projection down in the 3 space. But the problem is, if you wait till you get all this data, Dad's dead, right? Because you know, I mean, the data's coming in. I need to know today if there was a problem last night. Right? I can't wait until a year from now when I've got all this data and I can say, oh yeah, this was that problem right there. Right? So, this is the way the data is coming in. Some people's videos do actually play. I know, that's better. So this is the way the data is coming in. And so it's coming in temporally. Right? And we want to make the decisions as we get this data in. And so you can say this is just color-coded by the months. But you can see that, you know, something happened here, right? And formed a new cluster for a while. Actually, I think the guy had a heart attack, and this was during rehab, right? That the baseline changed in there, and it kind of jumped back over, and then there's some bad stuff going to happen down here. So our goal in this activity, this is, by the way, if you're interested, there's a lot of information on that website, eldertech.missouri.edu. This is the trend that the nurses told us happens to old people. You know, as they go along for a while, and then something happens, like they have a heart attack or they break a hip or whatever, and they drop down, dysfunctional ability. Then they go along for a while, they drop down, and they drive, you know, and then this is where we no longer have them with us. And so the goal is to square that life curve. You know, keep the plateaus longer and the drops shorter until the big one. You know, I mean, we're not going to, you know, it's hard for engineers to talk about people dying, but the nurses have no problem with it because they deal with it all the time. But you want the quality of life to be high, right? So we need to make timely decisions, right? So why am I calling it streaming consciousness? It's because, you know, we're very active people. We're engineers, computer scientists. We want to do stuff, right? So we want to build algorithms. And so sometimes in a rush to build these algorithms, we kind of forget about the underpinnings. You know, we kind of say, gee, you know, let's just not worry about the situation. Let's just get the next algorithm out. You know, nowadays, put it out on archive and stick it on get your code on GitHub. And, you know, and everybody starts using it, whether it's any good or not. You know, and so we should step back and do this. So, not as long as Jim, but I've been doing clustering for many, many years. And so he would agree, and essentially everybody agrees that there's 3 major questions about clustering. And so what my thoughts are whether or not these issues, these 3 questions that people deal with in regular clustering, do they come over into this idea of clustering data as it comes in instead of waiting till you've got it all? And if not, what takes their place? And of course, I don't have all the answers, so these are my random thoughts about this particular topic. And also, I like the title. You know, it's got a clever title. So here's my consciousness. And of course, I'm going to tell you the story based on what I do, you know, what I've done with Bez and others. And hopefully this will stimulate discussion and we'll move towards, you know, some things. And so I'm going to miss a lot of important contributions and approaches from the Computational Intelligence Society folks. So, and also, I know almost nothing about data mining. I mean, that whole community, you know, but a lot of this stuff happens in the data mining community. And so, of course, my Latin, that's also part of Latin. Okay, so, oh, hey, Pablo Uno, you recognize this one. It's the last summer school we attended. So here are the three questions. Are there clusters in the data? This is what we had a whole session on this morning, right? A visual method, so I'm going to do very briefly about that. The second question is, if you believe that there are clusters, how do you find them? Right? I mean, that's the algorithm part. That's what we all love to do. And I'm calling that the easy part because it's the most immediate thing that we can do, you know, is look for clusters. And then, of course, how do you know if the clusters you got are any good? Because there was a question at the end of Jim's talk about, you know, whether or not, you know, something about what's the hard part. And, you know, and part of his answer was, well, you know, all the algorithms are going to do their best. You know, you tell it, go find some clusters, and it's going to find them. You know, and it's going to come back and say, I'm happy. You know, because I found the optimal structure in this data. So back off, you know? And so, but the question from the outside is, you know, some clusters are better than other clusters. And so how do you know if they're any good? And that's, you know, these are things called validity measures that we use to do that. So here's Lotfi. He called me up one time on the phone, scared the daylights out of me when he did this. You know, he asked me to define a cluster, not a bunch of clusters. He said, how do you define a cluster? You know, and of course I gave him a glib answer. You know, I said, heck, I don't know, but I'll know one when I see one. Right? You know, like here's a great cluster right here. You know, cluster of buds. So, can you cluster these guys? So I was in Sanaz's country, you know, and we were sitting around the table there, and the answer is, of course, and Jim gave this great example of the decks of cards, right, and the suits and the, you know, hands. And how many clusters are there, which depends on the question, right? So I'm repeating what he said. How many guys enjoying a beer? One cluster, right, in there. Types of beer. There's actually 3 clusters there. It's hard to see, but there's 3 different types. How many nationalities are represented by the folks in this picture? There's actually 2, but you've got incomplete vectors because you can't really see this guy back here, and he could be a third nationality, but he's not actually, because I was there. Right? So it all depends on what the features you extract from the data, from your problem domain, and how you measure distance, right? Dissimilarity, right? Because if you change it, I mean, Sanaz had an example this morning where she changed from Euclidean distance to the L1 norm, and things change. Right? And so, you know, you've got to be cognizant of that if you're, you know, doing clustering. So, here are my rules. The data is going to arrive temporally, right? And time really should matter, although sometimes we don't let it matter. We only look at space, right? Feature space. Clusters have to be formed on the fly. We can't wait till we get a bunch of data and then do the clustering, because again, it's my rule, right? This just violates my principle for what a streaming clustering should be. It should happen as the data comes in. And we have to handle anomalies, right? We also shouldn't tell it ahead of time how many clusters it thinks it's going to find, because we don't know, because the data just keeps coming, right? So if you don't really know the problem domain, you don't really understand how many clusters there should be. You know, again, if I'm thinking about modeling an older adult, right, going through their daily routines, over time, they're going to change. The routines are going to change, and so new clusters will form. And so how many? Well, it depends on how long you live, right, if you're going to do it. And the other rule is, because we want this to scale up to, say, big data problems, is we're not going to be able to keep all the data. Right? When the data comes in, we're going to use it to update the model, and then we're going to throw it away. And we're only going to keep what we're now calling the footprint of the clusters. So in our cases, it's going to be the center of a cluster and maybe the covariance matrix, because we're going to model in this primary model, we're going to model them as Gaussians, you know. And so we can, and maybe we can keep the anomaly list, you know, things that don't fit into a cluster, because we have to look at them, because it might be that things start changing. They look like anomalies, they look like outliers, right? But what it really represents is the early stages of a new cluster. So at some point, we want to be able to say, oh yeah, that stuff you thought was an anomalies, those are now a new cluster. And so you have to be able to form a new cluster, and they're going to be formed out of anomalies, right, of the previous clusters. So we have to be able to save them, but that's going to be a small amount of data relative to the problem domain. Right? Pablo Neruda's house. Okay, so I never used to like to put these kind of outline slides on my talks, but I started doing it when I realized it was a good place to add goofy pictures. You know, so I put more pictures in the talk this way. All right, so you saw this morning, right? So these are two dissimilarity matrices, different distance matrices from two sets of data. And, you know, and the question was, should we try to cluster this data, and if so, how many clusters should we look for? This is a static problem. And of course, the VAT family was a visual way to do that. This was the algorithm, you know, and you know, if you do it right, you get things that look like this. And so this is the VAT images of those previous two dissimilarity measures. And, you know, I don't know, you know, to me it's pretty obvious how many clusters there are here, because you look for these dark blocks going down the diagonal. So, anybody believe that there's different than 3 in that first one? Okay. And here it's a little harder to understand, right? You know, is this like one big thing and this another one, or is there, can you see some substructure in here? So here's the data that came from. So sure enough, right, this one corresponds to this, right here. And this one, see, I know that there are 4 clusters here, or there are 4 classes here, because I made up this data. Right? These are Gaussian, little Gaussian clouds that this one's got this elliptical covariance matrix, right? So that it kind of goes up like that. So, can you extend this to this idea of streaming clustering? And he showed us this morning, right? Mostly with his gang down in Australia, and created this thing he called IncuVat, right? Incremental IVAT. Right? And this was the thing that Pablo Trace had to go fire off on his own, right? So this is the data. The interesting thing to me is that if you look at this image as it's growing, it's hard to see at any given time. You can't wait at the end of it. You can't say, "Oh, I know how many clusters there are." But at any given instant, you can look at it and say, "Oh, I see what it thinks right now." Right? So, I don't know, does it address question 1, how many clusters are in the streaming data set? Don't think so. Oh, this was his other one. Oh, this one doesn't, oh, yeah, maybe it does, yeah. All right, this was the other one that is a new version where they fixed the size, right? And they just resample. So this one actually does a little better job. But again, you know, at any given instant, we could stop it and look at it. So that's, I think, the key to this. All right? So, hey, if you've got them, the clusters, then, I mean, how do you find it? Right? If you believe that you're going to do clustering, and in the streaming world, that's you're already saying, I'm going to do it, you know, because that's the nature of this data. So there's lots of algorithms. So old-fashioned clustering, that's where you've got all the data. I'm going to tell you a little bit about the equations for some of that now. And everything depends on your distance matrix, blah, 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 right? Otherwise, you got to pick a value for the number of clusters, and you've got to deal with some validity measure. Right? Right. Now, okay. So here's the important thing. This is what a clustering of normal data is about. You've got a set X of data. Right? You've got a family of subsets of that data, and it's a crisp partition. If you union them up, you get the whole space. In other words, every point belongs to a cluster. Right? And they're mutually disjoint. Right? So that every point belongs to only one cluster. Right? That's a crisp partition. This, by the way, if you're into the set theory or logic, this is the law of the excluded middle. And this is the law of contradiction. So crisp partition satisfies those two laws from classical logic. And so you can specify a crisp partition by writing down the membership of each point into each cluster. And it's equal to 1 if you're in the cluster, and it's equal to 0 if you're not in the cluster. It's a characteristic function. And so to go to soft C partition, the fuzzy C partition, which I guess was first introduced by Enrique Raspini and used heavily for there, is you replace the binary value 0 and 1, you replace it by a continuous number between 0 and 1 with the property that for every vector, for every point, the memberships add up to 1. All right, so you share the membership among the clusters. Right? And really that's a probabilistic constraint. Right? If you're going to have them add up to 1, it's like they're the probability of being in the cluster. I mean, it's a different semantics. Right? But it's essentially that. And, and they're between 0 and 1. Then a possibilistic partition is one where you just throw away the middle condition here. You say, I'm not going to force them to add up to 1. Right? So you can have points that are perfect members of more than one cluster, and you can have points that have no membership. We call it typicality instead of membership. They have no typicality in any cluster. These would be the outliers. Right? The outliers shouldn't belong to any cluster. They shouldn't have 0.5 membership, right? So that you add up to 1. They should, if it's far enough away, it shouldn't belong to anybody. Right? Or if you're in a heavily overlapped area between two data clouds, you should have a higher membership in both of those than maybe 0.5. You might be close to the centroids of both clusters. So that's the most general form of a C partition, is this one. And this is just a picture to show this example, the idea that this point A, which is sort of equidistant between the two clouds, right? And this point B, which is also equidistant between the two clouds, they shouldn't both have 0.5 memberships in those two clusters. Right? This one should have much lower membership because it's much further away. If you put, in a hard case, in a hard C-means case, a hard partition, these 2 points have to belong to one or the other of those. In which case, it's going to pull the centroid away from the center of the cloud. Okay, so the hard C means is a very simple algorithm, right? You guess at C prototypes, C cluster centers, then you assign everybody to the closest prototype, update the prototypes, and then repeat until you converge. And convergence in this case is when the cluster centers don't move much. You know, so if they get into the right place, then you stop. Right? If you're not going to update it. So a very simple algorithm. And so this is just the membership updates are you look for the closest cluster center and you assign a 1 to it, 0 otherwise. The cluster centers get updated as the average of the points that get put into the cluster. And it actually minimizes this least squares criterion function in here, where these UIKs look like this, right? Zeros and ones. And every vector K has 1, 1, and everybody else 0. And so here's this data set, and I said, oh, cluster it with the hard C means using 3 clusters, right? Looks pretty dang good, right? These are the labels, right, of the 3 clusters. But here's what happened when I gave it this data set and said, I think there are 4 clusters in there because I know there were 4 classes, right? 4 Gaussian clouds. I said, go look for 4 clouds. And of course, what did it do? It took all of this, the Euclidean distance, took all of this, made this one, and it took this little nice compact looking thing and split it in half. Happens. Fuzzy C means, you just, you know, if you look back at this equation right here, you've got, right, just, this is that membership function, right, which was binary in the hard case. In the fuzzy case, this is now the fuzzy membership there, and this M is a parameter that's lovingly called the fuzzifier, that is a number bigger than 1, and what it does is it actually affects the partition values. You know, makes them either closer to 1 over C or closer to being crisp, right, 1s and 0s. So, you know, it's just a parameter. Most of the time, in most people that use the fuzzy C means, pick M equals 2, and that's because this is what minimizes that criterion function, right? You take the minimum subject to the constraint that the memberships have to add up to 1, right? So you use that to create, use that, take this membership function, write out the Lagrangian of it, take derivatives and set them equal to 0. That gives you necessary conditions. And you get these updates, right? So if M equals 2, right, this is a nice formula. Basically 1 over the normalized distance to the cluster center. Right, that's what you get in here. And then the cluster centers themselves get updated as the weighted average of the points. Right, now you have to add up all the points. You can't just add up the ones that belong just to you. Right, because all points belong to all clusters to some membership degree. Right, so you add them all up. And you get this thing is minimized only if this is true. So you use that in an iterative algorithm that looks just like the crisp C means, just like the hard C means. It just used different equations, right? Now this is a condition that happens if you land right on top of a cluster center, which almost never happens for real. But essentially, you update. Oh, where's it at? You update the UIKs, right, as in that equation, and then you use the new UIKs to update the V's, right? So you just do the same thing. You alternating optimization. And so here are the fuzzy partitions, right, that we got. Now this is a hard partition of the fuzzy membership. So the colors represent the cluster to which each point belongs to the highest degree. Right? You say, okay, if it's 0.4, 0.2, 0.2, 0.2, right, then you put it into 0.41. In this case. So, that's better, right, than the crisp one. But Jim also pointed this out this morning, is what happens if you change the initialization, right? Because you have to initialize these algorithms. And so I had a student do this. We took this little very simple data set, and I said, what I want you to do is run the fuzzy C means 100 times, where you just randomly sample the points to start it off. And so only 8 out of 100 turned out to give me this structure, right? Which is, of course, if he would have asked you as he would do that, he'd say, hey, Pablo, how many clusters do you see here? We would probably have all said 4 in this case. But in other cases, you see, put these two together, right here, split this guy in half, right there. And this is the final value of the criterion function. So of course, if you knew that, you would say, oh, this one's smaller than this one, so this is better, right, in some sense. But we don't know that because this is after the fact looking at it. And other times we got this thing. It's split this one instead of horizontally, it's split it kind of diagonally. So it's important to initialize properly. So that's why you should never run a clustering algorithm one time. You should always run an ensemble, right? Do it a bunch of times and sort of see what's going on. You can. But you can change this. There are hundreds, nay thousands probably, of variations of the fuzzy C means, right? And if you do a very simple one that's been around for a long time, this Gustafson-Kessel version, you can put in a covariance matrix into each cluster. So you can get Mahalanobis distance, like Gaussian type distance, right? And you can update it. It's got an update, so you do the same thing. You take derivatives now, not just with respect to the center and the membership function, you do it with respect to the elements of the covariance matrix. And so you get an update equation that looks like the weighted sum of a bunch of outer product matrices, which is how you build a covariance matrix to begin with. Right? If you've done, hopefully you've done that, some calculus class, or probability and statistics class. And this is what you get on that data set with the 4 Gaussian clouds, because of course it matches the model, right? I made the model to do that, so it does it. And so you see, it gets this guy in the middle. Okay, so then, what a crowd! Look at that guy. Raghu Krishnapurvam and I, we've discussed for years how to get rid of the sum to 1 constraint in the FCM. And there have been a bunch of ideas floated around, and we came up with this in '93. And so the criterion function is very similar. This is the FCM criterion function. You can't just throw the constraint away and then try to optimize the way you do for FCM, because then you'd say, well, the optimum, the minimum, would happen when all the U's are 0. Right? So make everybody's membership 0 in all clusters. Doesn't give you, it certainly solves that problem, but it doesn't give you very interesting clustering. So what we did is we tacked on a second equation. And actually, the way I thought of this is I saw the Hopfield neural network being used to solve the traveling salesman problem, which is a weird kind of thing. It's a dynamic network. right? And the way that they did it is they added some terms on there to try to force the conditions you want to only go to one city, one time, and make sure you get to every city. And so we added this extra term on here. So the first term, trying to make the memberships very small, right? The second term is trying to make the memberships close to 1, right? So we're balancing them with this. And these parameters, eta, which are for each cluster, 1 per cluster, right, is always been a sticking point for this algorithm, for this approach, because you have to find them somehow, right? They're not part of the optimization. They're weights that go along with each cluster. And so if you take this criterion function and you say, what's the necessary condition to have a minimum, right? Take the derivative, set it equal to 0, right? You get that the memberships look like 1 over 1 plus the distance squared to some power, right? So the farther away you are from the cluster center, these are the cluster sides, the chain notation. Those are the cluster centers, right, in this case. The further you are away, the smaller your membership is. Right? The closer you are, the higher your membership is, or typicality, in this particular case. And the center update looks exactly the same as in the FCM. The weighted sum of the vectors themselves. And of course, how do you find eta? People have complained about this ever since 1993. Raghu and I came up with some iterative scheme, to say, oh, you can update eta each time during each iteration, right? Some people just pick constants. Works sometimes, but many times they pick the wrong constant. They pick one too big for the data that they're trying to cluster, and then they say, see, this algorithm doesn't work, right? Because it didn't work for my choice of parameters in there. This was our way around that in the 93 paper, was to say, well, look, each iteration, update the eta based on how the points belong to the clusters in there, right? And the latest work is this thing we're calling dynamic eta, which is an optimization of eta. And it kind of works like this, is that you take the point and you recluster it using the PCM for a particular value of eta, and then you do it over and over and over and over and over for all different kinds of etas, and then you plot the average typicality in that cluster, and we pick it where the knee of the cluster is. So we have a way to pick what we claim is the best data based on the data that it's looking at. Anyway, that's a nice paper. Okay. And so here is this famous data set from Jim's 1981 book, the butterfly data. And here's where the centroids end up with the PCM. And that point in the middle was always the point that we focused on. In a hard C means it has to belong to one or the other of the two clusters, right? And so it pulls one of the cluster centers towards it, right? In a fuzzy C means it gets about a 0.5 membership in each, so it sort of stabilizes in this particular case. This is that guy from the Netherlands calls this X-liers or something like that, or inliers instead of X-liers. And a PCM, that point gets a very low membership, very low typicality in both clusters, so it really doesn't affect the clustering much. And then if you stick one outlier point onto the butterfly data in here, this is what a run of the hard C means looks like. It captures this, and that's the cluster center, the red circle, right? And in the fuzzy C means, because it's got 0.5 membership, it pulls these things just a little bit up. And the possibilistic C means this thing has membership of like 0.02 or something in both clusters, so it doesn't really affect where the cluster center ends up. Yeah. So, what about streaming partitions? Right? Does it make sense to have a partition of the streaming data? In some sense, that's what the IVAT sort of does at any given point. It sort of shows you visually what a partition might look like, right? Although it doesn't have labels on the partition, it's got them just in your eye. So, by definition, I'm not keeping any of the data. So I can't really compare. If I'm not keeping the data, how can I keep the membership array, right? Because a membership array, the partition, has C rows, one for each cluster, and N columns, one for every data point. So if I'm not keeping the data, I can't keep this thing either. So we shouldn't do that, right? Because they'll keep growing. And that was the difference between those two versions of IVAT, IncIVAT, that I showed and that Des showed earlier today, is that you can only keep sort of a snapshot. Somehow you've got to roll a window along, or you've got to resample or do something with it. So, okay. So some people have tried this batch streaming, right? Where you bring in a bunch of data, and then you cluster, and then you bring in another bunch of data, and you cluster, and then you try to say, are these clusters the same as these clusters? Right? And then you try to cluster the clusters, in a way. Right? So you try to reconcile. I mean, it's certainly okay, but I'm not, I've got enough problems already. I don't want to bring that one on myself, All right. So, the reason I told you about those other algorithms in the standard case is because you can use these models, the same models, in a streaming mode if you can make them incremental. Right? So if you can do something that allows you to incrementally update, then you can use these different kinds of models. And of course, the type of information you keep will guide the particular process. And so you get a lot of different flavors right in here, of these streaming algorithms. Even ones with a little cherry on top, those are the possibilistic ones, I think. The ones that have the cherry on top. So, initialization, we already know that's a big problem. Right, so you got to find a way to start the process, and of course it's different than if you have the whole data set, right? You only get a little bit of it coming in, and you got to start it up. How much of the stream can you keep, right? That's a question we all have to answer in this. And of course, do the soft assignments make sense? Are they useful in the approach? And how do you deal with outliers? How do you handle them? Because, of course, if you're not careful and you spawn new clusters every time you get an outlier, which is what many of the early versions of streaming clustering did, right? They would say, well, if you're not close to the data I already got, you must be the beginning of a new cluster, right? But if it's really an outlier out there, then you've got a cluster now that's got one point in it, and nothing will ever update. And so if you've got noisy data, lots of outliers, you have, hundreds of clusters potentially in here. And of course, and then one man's cluster, one man's outlier is another person's prototype, in there. How do you figure out whether you need a new cluster from the data you've got? How do you even know it's working? I mean, again, all these algorithms are going to work. I mean, they're going to do something. And they're going to tell you that they're doing a good job because they're doing it to the best of their ability. They all want a participation award. Right? But you want to know who the first place goes to. Right? Should you merge clusters? I mean, this is the question. If you saw in that second data set that Jim showed this morning, there were those 5 clusters, and then the four clusters on the edges got sort of filled in, right? And it looked like they became one big giant cluster, each side. And so that's sort of emerging, but does emerging only take place in feature space? Or should it take place in time? Is time, the fact that they occupy the same physical space, if they come in at different times, maybe they shouldn't be merged together. Maybe they ought to be different, I mean, these are questions we all have to do. And drift is a problem. Things that change slowly over time, right? You could just, grow and grow clusters. All right, so many questions. And this is the big question. The two of us have been debating this for a while now. Does this even make sense, the phrase streaming clustering? Because all of the models that we've looked at, including the ones we've built, all actually assign a label to a point that comes in. Right? Each point comes in and we say, okay, here, we're going to put you in this cluster. Or you're an outlier. Right? Something like that. So it's actually a classifier. So we started thinking maybe we're looking at it with the wrong lens in here. Maybe it shouldn't be a clustering problem, it should be a classification problem. So actually I think it's like, what happened? I started calling it clustification, which of course, he doesn't like that word, but it would be a Latvizade word, clustification. All right, so this is a CI workshop, right? Summer school. So we ought to talk about how CI plays in this game. So I don't know about any evolutionary algorithms, multi-criteria, many criteria, or no criteria that do it, but it sounds like a challenge to me. I don't know, I like this term, incremental ants. I don't know, that sounds like a cool thing, but I don't know. But we have one of the pioneers. This is Pablo Uno, right here, introduced me many years ago to neural gas, right? A competitive neural network. But you can't just use neural gas itself because you got to have all the data. It's an iterative process. Right? But you could try this growing neural gas as the data is coming in, but you got to have a way to get some prototypes to the outlier regions. But if you can't just put them out there, because if you do that, they're stuck, and they're never going to change. So the adaptive resonance theory will put things out there at these spots, but you have to be able to kill them if they don't get reinforced, right, with Hebb's rule, if you've taken any of this neural stuff. Right? So this is what the growing neural gas produces, the general, if you've got all the data. Right? It just distributes prototypes within the data structure that you've got. Right? So it's not looking for centroids in this case, it's just looking for a code book that you could represent the data set with, and it does a pretty nice job. And it chops connections if the connections need to be chopped. And it's got a natural way to do that. And so I challenged one of my students Waylon actually, to see if you could do this with some data. He would have to be really careful about the parameters he chose in here. But you can see what it does is, and he wasn't very careful about keeping the scale the same. But when it finds it, when an outlier comes, there should be some coming over here soon, it'll stick a prototype over there, but then, oops, then it has to like break this connection. Once you I hope it breaks the connection. Come on, okay, okay. So anyway, so you can actually have a neural streaming, clustering, classifier kind of thing. But here's what we did. We came up with one that, of course, I love the PCM, right? So we use the fragile part of all clustering algorithms is initialization. Right? The PCM is good with that because it identifies outliers. It's good, robust against noise. Right? So we get some data in, and we run the PCM on it, or this other thing we like, this sequential possibilistic one means, to look at the outliers, and then we get an initial cluster center for the clean data. So we look for the outliers, hold them off in the anomaly list, and initialize, and then we just use Gaussian mixture models. Right? I think Jim said he's going to tell you about EM tomorrow. Right? And so this is essentially, and the reason why we like it is because you can incrementally update the mean and the covariance matrix of a Gaussian one point at a time. Right? So we just use a model of that, and then we use the possibilistic one means to look for new structure, right? New classes. Right, okay. So here it is running. You can see these ellipses are the drift, right? As new points come in, we're changing the center and the covariance matrix. So this is two-dimensional data, of course, so we can see it, right? And this is what happens. And these are the anomalies that never got absorbed into any of the clusters. They weren't dense enough to be called a new cluster, and so those are the things you want to alert if this is from a person, you want to tell the nursing staff, go check, you know. Right. Okay. So here's a data set. This is similar to the data set that Jim showed, the weather data, you know, the Heron Island weather data. And you look at this and do you see any structure in this data? You know, would you say this is a good candidate for clustering? You know, I mean, I look at it, I say, gee, it's hard to think of that there's really clusters in there. But this is how the data comes in, temporally. Right? So here's a case where actually seeing it coming in one point at a time actually shows you that stuff is going on over here. Right? And then what's going to happen is it's going to kind of, with a few anomalies, it's going to kind of do a thing here. Right? It's going to jump over here. And what that represents actually, this is temperature, humidity. So this is, you know, mild, if you want, mild weather. Right? Then it's going to jump over here, it gets colder. Right down here, low humidity. Right? And then it starts snowing, right, up here. And so, you know, from that standpoint, we of course argued, because it's on paper, you know, we argued that this is the final clustering structure that our algorithm must produce. And it produced clusters. These are the covariance, you know, the covariance ellipses that at the end, after all the data came in. And these are three other sequential clustering algorithms, very simple ones, that ran on this, and they tended to slice these things horizontally for some reason. You know, I mean, given the fact the way the data comes in, I'd argue that this is the better cluster. I mean, you know, that's the problem with clustering, is you don't know the actual answer, right? I mean, not classification. So, in ElderCare, this is kind of the way the data is. And what we want to do is we want to find when something is coming out of the cluster, because that's going to signal something going on with this older person. Right? When you're coming out here, this stream coming this way or that way. And what we'd like to do is we'd like to anticipate it before you actually become an anomaly. We'd like to do early illness detection. So we'd like to know that, hey, you're coming towards the boundary of the clusters you've got. That's our goal. Yeah. And so we've got a way, based on this streaming mode, to suggest different warnings that can be sent to the clinical staff. Right? And we do it based on typicality. So we look at several points of data and we say, sequentially is the maximum typicality in any cluster going down. And if it goes down, we're saying you're moving away from the cluster. So maybe it's time to signal a warning in there. Yeah, okay. And so these are just made up thresholds that we pick. And we also measure the angle, that the vectors are moving, right? We use the cosine of the angle because it's easy to compute. Right? And so here's a person. This is the principal component projection into 3-space. This is 20-dimensional data projected into 3-space. And again, this is retrospective. This data is already, we have it, because we've been monitoring people since 2005 at this elder care facility. Oh, there it is coming in. And this is this other nonlinear projection called TSNE, projected into 2-space, which actually is pretty cool. This was the early baseline in here, 3 years worth of data in here. Then I moved over here where there was some cognitive impairment. We got, something going on there. Had surgery, right? And then had some swallowing problems and back pain. So we're moving around inside this feature space, but this really isn't, the place is up there in 20-space, right? Not there in 2-space, but it was a nice diagram put up there. But you can see how the data is sort of coming in. Again, this is the TSNE projection of that. So we went back into the electronic health record, and we said, for this particular guy, what were the bad things that happened? Right, so we went through, we're trying to do this automatically, but we had one of the nurses go through and pull it out. And these are the dates in which there were things that happened that had bad flags when we issued the warning. So our system that runs at this facility has a one-dimensional numeric warning that's sent out. And that's all these little, what are these colors? Turquoise, I guess, right? Turquoise colors. The black lines are the bad things that happen, right? These black lines. And the other colors are our weak, medium, and strong warnings in there. And this is just with our warnings in there. So you can see we have warnings that predated close to this bad thing that happened, but yet far enough ahead that we could have maybe, had we been using it, we might have been able to do something. This one, I don't know. I mean, here's one that looks like the warning came after the bad thing happened, but, again, there's some parameters we got to tweak. But I mean, it shows that this idea of trying to track the trajectory of a streaming clustering data has some value in real life cases. Whoop. I guess I should leave it on. Well, maybe it'd be better if I left it off. Yeah, so problem number 3. Do you know if the clusters are any good? Right? So, traditionally, there's a bunch of these. You either have to, if you want to be a person that does unsupervised learning, you have to either create an algorithm, the cluster, you have to create some kind of visualization, or you have to create a validity measure. It's like a rite of passage to get in there. So there's a bunch of these things, and almost all of them are based on, as Jim pointed out, the compactness of the individual clusters that are formed and the separation between them. Right? So this is one of these things. There's the separation, is the minimum distance between cluster centers. That goes down in the denominator. And then the numerator is a measure of the compactness of each cluster, of the clusters. And so that's this one called the G-Benny index. And so what you're looking for is a number of clusters where this thing sort of has a minimum. But, they don't behave very well. You cluster it from 2, 3, 4, 5 clusters. And, this is the clustering that, for this data set, with 3 clusters, that looks pretty good, right? So, we get it, this is a streaming data that we set up, it's a two synthetic data sets that in this particular case, all the data came in sort of one cluster at a time. I mean, we made it really nice, you know, from the bottom to the top. And this one came around the circle like this, except for the middle one, which got some points each time. Right? And we used that because what we did, Jim and Omar and I, built a streaming version of the Davies-Bouldin index, and forget about the multiple curves, just look at any one of them. What happens is the new cluster forms at each of these red lines. Now, each cluster in this case had 100 points in it. Right? And so what you see, if you look at, this is one of them blown up, one of these little gaps in here blown up. So what happens is, when the points are coming in to the clusters that already exist, the measure is pretty stable. Right? It just keeps saying, okay, I maybe got a few more points, but I'm you know, doing okay. Then what happens is the anomalies start coming in. Right, the new things that are not in any of the clusters, and this incremental value goes up, right? And then right here it drops when the new cluster is formed, right? And it starts over again, right? So you can see this sort of stair-step thing. So it's not a validity measure at all. What it's doing is it's telling you how the process is behaving. Right? So you should look at it more as a way to understand the clustering if you can't see it in two-space. Right? If the clusters are 20-dimensional. Oh, and on that round one, they had a little skinny line right here. Right? But if you look at it, the skinny line is, if you blow it up, the skinny line is also one of these things that kind of drops. And pay attention, there it is. So here's the validity measure. And you see, it keeps going up and up. And then right about now, it's going to have enough density to form its own cluster. And that's when, ping, you know, so it only dropped because after, you know, 10 points, it said, okay, now I can do the clustering. Right? So we ran it on some benchmark data in 64 dimensions, right, where you can't, I mean, I can't show it to you. Right? But this is what one of my grandsons, quite a pirate, yarn. You know, and you see it's behaving roughly the same way, right? So you can kind of say, oh yeah, this must be Gaussian-like data because it's behaving this way. Right? And we projected it down into the two-space just to kind of get a feel for it. That's my other one of my other grandsons there too. Yeah, we do this pirate thing, you know. So you kind of see, this is, you know, the two coordinates in there, and you see this structure. But I mean, this is not the same as the 64-dimensional data. So the point is, you're going to run it on the 64D data. Okay, what's that? Oh! Cigar boys. All right, so you remember IncIVAT, right? So it actually is one of these same incremental measures to try to understand the process. You know, we haven't figured out quite how to exploit that yet. I mean, that's an open question. Is how do you automatically do something with it? Yeah, okay, good. All right, so this is something that probably you'd like to see. Takeaway thoughts. That means it's almost over, right? Okay, clustering is cool. I had a friend of mine who I trust a lot said to me one time that you have to be more adventurous to do clustering than to do classification because you don't know what the answer is. Right? With classification, you know the answer, and you're just trying to get an algorithm to give it to you. Right? Clustering, you don't know. It's unsupervised. Right? Streaming clustering is good. And new challenges, but new opportunities. Right? Dissertations. Think dissertation. Right? Or papers at some exotic country like Chile. Huh? Oh, wait a minute. Oh, like the U.S. Okay. The three problems of classical clustering need modification somehow, right? You know, I'm giving you my thoughts about it, but I'm not an expert. I'm just dabbling in it. And so there's always room for new algorithms, new techniques, new insights. You know, you need those young, fresh minds to do that. Right? Yeah, to write a passage to make one of those. So, and then we got to figure out how do you do clustification? You know, how does this, can we recast it? I'm the bottleneck right now on a paper. I've got a bulk of a paper that we're going to write on streaming classification. But it's sitting on my disk, waiting for me to work on it. So it's essentially all from me. I want to thank Pablo Trace for inviting me, and of course Pablo Uno is always in there, letting me ramble along. And of course, thanks to all of you for listening. And it's really hard to separate the two of us, right? If you look at that, we're always in the same cluster, right?
We have time for questions. Questions, preguntas, pueden ser en español.
Here you go. It's always good to have one.
Thank you. My question is, how sparse do you need or you require in percentage of the total input data stream in order to do a good class clusterization?
I'm sorry, let me see that. Did you ask how much data do you need to start?
Yeah.
Yeah, okay, that's, yeah.
Or a spike that you require.
Yeah, so this is a continuous battle with my graduate students because, of course, they want most of the data before they start because it gives them the best Gaussian clouds to create. But, a rule of thumb in our elder care is that you should be able to start the process with either 2 weeks or a month of data. I mean, in the real world, in this real case. So in our case, since we make one feature vector per day, so we should be able to do it with 30 feature vectors to get it started. It's probably going to be one cluster, which is okay. I mean, starting a streaming mode with one cluster is perfectly fine, as long as the cluster's compact, right? That it's okay to do that because the new data will start looking like outliers and then it'll become a new cluster and go on. But yeah, I mean, that's really, initialization is the crux of this. And I don't have the final answer. All I have is sort of a rule, a heuristic that we've been using. It was actually cool in this room when I came in this morning.
Yes, it was.
Okay. Thank you. Another question? Yeah.
This is siesta time anyway. Here. Igor's got one.
You said that you have those 20 features, for example, and you did this in a three-dimensional space. So
No. We clustered them in 20 space. I was only showing you 3 space.
Okay.
Yeah.
What about this example with sequential clusters? If you have just data coming to a certain cluster and then to another one, you didn't try to, this example.
Yeah. So this is that's a very astute question actually that I wasn't going to answer until you asked it. This data came in the sequence that I showed. So it came around, the circular data started, went around like this, except for the points in the middle. All right, came around, put a few points in the middle. Next one, put a few points in the middle. So it actually came in the sequence that we wanted because it was synthetic data. So Larry Hall, I think it was, asked me, well, what if you just put them in a random sequence? Well, of course, it's not going to, there is no clusters then. I mean, you know, if you, sure, we did it, and of course it gave me one, like that one, the linear one that went up the line, it gave me one big giant cluster, you know, with a very high eccentricity. You know, the ellipse was very, very tight. So, yeah, so if the data is coming in, you know, just kind of all over the place, then, you know, it's sort of, you can't do streaming clustering with it. You might then, you know, the best you could do is hope to collect enough of it and do regular clustering.
Because this example comes when you are doing regression problems and doing the streaming clustering. So it comes in different regions. If it's non-linear, then you would get this kind of shapes.
Right.
And then, I mean, in this case, you didn't do the merging. No merging was used here in this example.
I didn't merge clusters in this particular case, but that would not be the problem that you first stated for me. The problem that you stated would be I would get one big giant cluster that maybe I should split, right? So if you had a criterion for saying this cluster is growing too big, you know, you might, I mean, there are algorithms that do that would say, okay, I'm gonna chop it, you know, into sub pieces, and then restart the problem. And that would be might be one way around that. If the cluster seems to, but again, then you have to answer the question: what does it mean to be too big? You know, I mean, I think I've traded one question for a different one then in that particular case. But yeah, the order of the data is important, right? And so that's why in the elder care case, it makes sense to, you know, people are, oh, wait a minute, he's already got a microphone here. This guy's got a microphone. Go ahead.
Hi.
Then we'll go to you.
Thank you for your presentation. I have a question related to the elder care.
Yeah.
How do you take into account both the similarities and differences in having different people, because the nominal state of every person is going to be different.
Absolutely.
There's going to be some similarities between them.
Right.
How do you account for that?
This has plagued us since the very beginning, because so much is dependent on population statistics, and that doesn't work because everybody's individualized. Because if you look around the world now, the big push is to precision medicine. Right? They want to create the medicine for you and not for the population, right? So they want to tailor it to individuals. So all of the stuff we do in the elder care is a single person model. So everybody's got their own model, their own baseline, and so what we're doing is we're looking for changes in the baseline. We're not looking for some absolute baseline. We're saying this is the way you normally function. Have you changed? Right? That's what we're trying to look for.
All right, but is there any way to use that information from different people in order to improve?
Yeah, yeah, certainly. I think you can. We started looking. We have something we're calling the Transfer Learning PCM. Right? So we've got a model where we build a PCM clustering. This is a static model. But we build a PCM clustering where we got lots of data for someone, and then we take that model as the initial states for a new person coming in. So we transfer it over.
Then we sort of fine-tune it.
Well, that's the hope. I mean, if you read the paper, we did it. Okay.
Hi, I didn't know this method, but I use one called dbScan to detect
Yes.
cluster outlier. So, do you know which are the difference or which is better?
Yeah, dbScan is also a density-based clustering. The differences, I'm not sure I could do it, but yeah, we're trying to compare right now this with dbScan. Or DenStream, yeah. Yeah. So, yeah, I don't know the differences.
Okay, I have a question.
Okay.
Since you have a sequence of data, there's some structure, not random, then have you thought about linking this with forecasting?
Well, that's what's kind of our early warning system is based on that. The idea being that we want to be able to predict when a stream of data is moving out of the normal cluster structure. So, you know, it's still up in the air about how good this is really going to be. But right now we've got the clinical people looking at the warnings that we're issuing, but it's all retrospective right now because so we know what's happening. So they can go back into the medical record and look to see if we did a good job predicting. And then, I mean, our goal is to stick it in live, you know, in the daily monitoring, and then, you know, and see how well it does, you know.
Thank you. Another question? Already time. One question?
Oh, no.
No?
No?
Well, we thank Jim again.
Okay.
Thank you.
Again.